Okay, the question we're going to try to answer today is, does acceleration cause time dilation? And the answer is no, and we're going to show you that. So the example is going to use two planets. The first planet has the mass of the Earth and the radius of the Earth. The second has 10 times the mass of the Earth and a radius that's 3.3 times the radius of Earth. Given these numbers, what is the gravity or acceleration at the surface of the planets? Well, applying Newton's formula, we get 10 meters per second squared on both planets. So they both have the same acceleration at the surface. This is because the radius is larger for the planet with more mass. What about time dilation on the planets? Well, we can use the Schwarzschild radius to calculate the time dilation. And on planet 1, when we plug in the numbers, we get a very small time dilation. And on planet 2, if we plug in the numbers, we get another time dilation. The key is that they're not the same. So even though they have the same acceleration on the surface, the amount of time dilation they're experiencing is different. So just to reiterate, let's take a look at these planets again. They are both experiencing 10 meters per second squared in acceleration. However, their clocks are moving or experiencing different times. What else can we look at for these planets that might help us? Well, one thing is escape velocity. We can calculate the escape velocity using the equation given. When it is applied to the first planet, we get an escape velocity of 10 kilometers per second. And on the second planet, it's 19 kilometers per second. So the planet with the larger mass has the greater escape velocity. Now, what's interesting is you can apply the escape velocity to a standard special relativity time dilation equation, the Lorentz equation. And this will give you the exact same amount of time dilation as the relativistic equation we used previously. So the key is it's whatever the velocity of the frame of reference you're in determines the amount of time dilation, whether that's actual velocity or escape velocity. Now, here we're just going to run the numbers to prove that what I said is correct. And indeed, the first one gives you the same time dilation when you apply it to the Lorentz transform. And the second equation also gives you the same time dilation. So it's all about the escape velocity when it comes to an accelerating frame of reference, not the actual amount of acceleration. What are the implications? Well, the gravity well is like traveling at the escape velocity through space-time. Acceleration does not give you time dilation. And a lot of physics popularizers oversimplify. So thanks very much. And I will just show you that there's a lot of oversimplification in popular physics, as demonstrated by this one MIT's professor's experience dealing with a show that was put on public television. Thanks very much.
Might just add that there was a series, this is just an aside, but I guess broadcast last year, there was a 4-part series of Brian Greene's Fabric of the Cosmos that was broadcast on PBS. And the interesting thing about that, which is relevant here, is that he tried to illustrate time dilation, and he did it by having a sort of a parable of a person sitting in a chair and somebody else carrying a clock over his head walking towards the person sitting in the chair. And the camera showed what the person sitting in the chair would see, and it showed the clock running slowly. That's wrong. In particular, for this example of the person sitting in the chair and the clock coming towards him, that's exactly what we're going to be talking about. That is the Doppler shift. And what we'll find is when the clock comes towards him, he will see a blue shift, not a red shift. He will see the clock running faster, not slower, the opposite of what was shown in the TV program. Might just add that Brian Greene and a bunch of people here at MIT, actually, I was involved and so are some others. There's a number of MIT people on this program. So we had ended up having a long conversation with Brian Greene about it by email. And everybody at MIT thought it was just plain wrong. Brian Greene actually took the position that it was very intentional on his part, and he was just trying to illustrate the time dilation effect, and he didn't want to talk about the Doppler shift. And since he didn't want to talk about it, he could ignore the fact that it was there. And we all thought that was bad pedagogy, but we never convinced Brian.